The Treachery of Images. Bayesian scene keypoints for deep policy learning in robotic manipulation. Representation learning methods can speed up image-based policy learning by orders of magnitude. However, current approaches have critical limitations. Among other things, they struggle to correspond visual features across image scales. Yet, this is a common requirement, for example, when learning from a wrist camera, as shown here. Second, they usually assume full observability of the scene. Though in practice, objects can be occluded or lie outside the field of view of the camera. To remedy these problems, we propose a two-pronged approach. First, we train a semantic encoder network based on dense object nets to find likely correspondences between images of different scale. Using image augmentations, we train the network to generate multimodal localization hypotheses if the context captured by the image is insufficient for unique localization of the feature. Second, we propose to make a paradigm shift from image representation to scene representation. A single image might be ambiguous and lack scene context to localize features or objects. We therefore integrate the localization hypotheses of successive observations using a Bayesian filter. This allows us to disambiguate multimodal localization hypotheses and track occluded or out-of-view objects. On top of that, we retain the generalization capabilities of dense object nets and generalize to unseen task environments and class instances. Notice how our method generalizes zero-shot to new fruits and bowls, and that from being trained on just one instance per class. Finally, the spatial consistency enforced by our base filter allows to track the original object, even if a second identical object is added to the scene. In our real-world experiments, we find superior efficacy of our method for policy learning compared to other representations. Moreover, our base filter improves over the bare correspondence model in a number of important ways. First, the integration of multiple observations increases the robustness and accuracy of keypoint localization, especially at short ranges. This aids the policy in precise grasping. Second, our base filter successfully tracks multiple scene objects, even across prolonged occlusions or the object lying outside the field of view. Note, for example, how our method is able to solve this pick-and-place task using only a wrist camera. This is despite the grasped object heavily obstructing the view of the camera. Third, our correspondence and policy models generalize to a multitude of novel situations, all without additional training. For example, our policy models can solve the same tasks in cluttered scenes. In addition, our correspondence model indicates high semantic understanding. For instance, it generalizes from the white bull to this wooden bull, despite only having been trained on the white bull and no additional class instances. Fourth, our method is robust towards adversarial disturbances like manipulation of scene objects. Finally, our method is invariant to the task environment. Despite only having been trained on the table shown previously, it generalizes to these varying kitchen environments. In conjunction with its ability to learn from wrist camera observations only, this capability makes a method attractive for a number of important applications, such as federated learning, flexible deployment outside of research labs, such as in homes, and in mobile manipulation.